Well, thank you so much. Well, first of all, thank you, the organizers, for organizing this nice meeting with these very interesting topics and such a nice place. So I'm really happy to be here. So I'm going to tell you about, we've seen about twisted bilayer graphene, but I'm going to focus today on the normal state of twisted bilayer graphene, and you will see why. So first of all, I want to introduce my collaborators. Anusri Datta was a postdoc with us until a year ago or so, and she's now in Paris. Then Alberto Camhayi is our collaborator from Argentina, who's an expert in dynamical mean field theory. And then Lenny Vascones is my very long-term collaborator. We have worked in many different things together. Okay, so let's start from the beginning. This is graphene, you all know it. We have two inequivalent carbon sites, A and B, and now we put another layer of graphene on top and we rotate it, okay? So as we rotate, you've seen this many times, that some superstructure is forming, okay? And this is what we call a moire pattern. And in this moire pattern, we can see some areas where there is AA stacking and some others in which we have AB stacking. And this is illustrated there. The AA stacking areas form a triangular lattice. And we have a very large unit cell, which is, whose length is proportional to the inverse of the angle. So for this, the angle is like 7 degrees, so the superstructure is not so large. But for a magic angle, which is around 1 degree, the superstructure is really, really large. The unit cell is very, very large. It includes thousands of atoms. If you look at the reciprocal space, this will be the Brillouin zone of each of the two layers. But now, because of having the two together and twisted, we have these mini Brillouin zones here. One that is related to one K point and the other that is related to the other K point. And you have the Dirac cones here, okay? So you can plot this like that. You have the two Dirac cones that are very close together. And if we don't allow any hopping between the layers, you could have just something like that. But in the moment that you switch on the hopping, then there is some changes in the bands. And at the end, you can get this interference, well, because you have a very large Brillouin zone, and you have a lot of folding of the bands, and this interference gives rise to these very flat bands. And this occurs at a particular angle, which is called the magic angle. And importantly, we have two flat bands per valley and per spin, okay? So we have a higher, well, we'll see that we have up to 8 electrons that we can fill in these flat bands. Okay, so this is the band structure from some continuum theory. And this is for the magic angle, which is around 1.1 in this particular case. You see these very flat bands here, and these are the remote bands. And the black and the red come from the two different values of the original graphenes. If you zoom in, these flat bands, they have some dispersion. We again have here the two valleys, the valley degree of freedom. These are the original Dirac points that are protected due to the symmetry of the system. It has C2T symmetry. And this would be our charge neutrality point, where the Diracs are. Okay, so that is what we are going to consider zero filling. And now we can move with a gate. In this case, we can move from -4 to 4 in filling. Okay, so that would be the range of fillings that you can achieve by gating in this case. No, so we have 8 because we have as I said, 2 valleys and the 2 spins. Okay. So in here, the idea is that we have these very flat bands. We have seen this before. This implies that we have a very small kinetic energy, and then the electron-electron interaction you can dominate. So when well, in 2018, when the superconductivity and insulating phases were observed in these materials. This was the kind of mantra, no, that that we were hearing all the time, no, that here we would expect, we should expect to have very strong correlations. Okay, so since then, the field has grown a lot, and there are so many things that have been observed, so many states that have been observed in these systems, not only to by graphene, but other moire systems, and also some graphene multilayers without any moire. You also can find different correlated states. So the first ones were this is a paper by Efetov that came out a little later than the original one from Pablo Jarillo's group. But here you can see the correlated states happening at interior fillings, the superconducting domes in between. And after that, many other probes came out. So there were the observation of cascades. I will talk about this a lot later. But many other correlated states, like intervalley coherence, ferromagnetism, interior quantum Hall effect, fractional churn insulators, charge density waves. If you're interested in that, because I'm not going to talk about all these correlated states, there is a recent review on Moire that takes, I mean, you can see all the literature there. Okay, so from all this, I'm going to care about the role of correlations. And in fact, I'm not going to go to all these correlated states, all these ordered, symmetry-broken states that have been observed, because what we wanted to explore is what happens at the temperatures above these order states. Okay, that's the idea. So the first signature of strong correlations were coming from these scanning time macroscopy measurements, in which they can tune with a gate. They can tune the chemical potential in these flat bands. And the first observation was this is the IDV plots as a function of bias that allows you to explore, to move the chemical potential. And then what was observed is that when you have fully occupied flat bands, so if you put your chemical potential here, then you have some signatures that tells you where your peaks are. Okay, this is coming from the band structure. And if you are in some other filling, so a partial occupied flat bands, then you have something completely different. So what we see here is that there is not a rigid band shift of the bands, and this is one signature of strong correlations. Another observation was the fact that when you apply this bias gate and you you change your filling of the bands from -4 to 4, there are dips in the conductance at the interior fillings. Okay? And this is something also that we expect from strong correlations. So these are bands in which, in principle, if you are completely empty or completely full, you have a band insulator. But if you are in the middle and there is no strong correlations, you would expect it to always be a metal. But there is something happening at interior fillings that is changing this result, no? And is giving you dips at interior fillings. Okay. So, and later, like 1 year later or so, there were more accurate STM experiments in which they could tune all the gate voltage and the bias to see what was happening with the spectral weight. And you can see, so this gate is proportional to the filling. So here it's equivalent. This would be like being in the charge neutrality point, and then we move towards filling with electrons or filling with holes. And they were measuring with the tip on the AA regions or the AB regions. So you see that there are different signatures that you can see from the different parts. And what you see here is that there is a strong spectral weight reorganization. So you can see that there are like flows of the spectral weight moving, and they reset at interior fillings. So we have something happening here at charge neutrality point, and then at 1, 2, 3 filling, And this, well, it's not so obvious in this case here, but there are also other plots for different samples in which you can see more clearly here as well. So there are always these resets happening at particular values of the gate that correspond to interior values of the filling. So we see this different behavior also at CMP, and we also can see some oscillations of the remote bands. Okay, so these bands that are not that are away from the flat bands, they were also showing some oscillations, and they can be seen here on the AB side when you put the tip on the AB side. And well, and one important thing about this is that these cascades were measured at 6 Kelvin, but if you they have been also measured at higher temperatures, and here it is for 20 Kelvin, and there are still signatures of what is going on here. So this is something that is surviving up to high temperatures. Another signature of things happening related to correlations comes from the inverse compressibility measured with a single electron transistor. And this, again, the filling of the bands, and we see there is a symmetric peak at 0, and there are resets at every interior filling, and there is this asymmetric shape of the resets. And this is also, I don't remember the temperature for this, but it also survives up to very, very high temperatures, so tens of Kelvin. These kind of cascades that were observed in 2020 were primarily interpreted as coming from broken symmetry states. So we saw this picture yesterday from Jenny Law, in which it was assumed that what was happening here is that every time that you hit an interior filling, there is some broken symmetry. So you have this degeneracy of spin and valley, but every time that you hit an interior filling, the system prefers to fill one of these degrees of freedom, and this is what they call Dirac revivals. Okay, so that was the interpretation of all this. However, the temperatures at which these broken symmetry states appear are lower than the high temperatures at which these cascades, both these and the STM ones that I showed before, survive. Okay, so that was the motivation to look at what happens when you don't have the broken symmetry states, but you are above their temperature. Finally, also the resistivity at interior fillings, it changes a lot from sample to sample. So in this paper, you can see a few samples, and the results are slightly different. But what you can see is that there are signals of high resistivity at different interior fillings, and there are even cases in which, for instance, here at 2, this state decreases its resistivity, and then it reappears. No? So it really is surviving all this resistivity at interior fillings, surviving up to high temperatures. Okay, so this observation that we have the cascades and insulating behavior well above the temperature at which we expect to have broken symmetry states, made us ask a question, no? What kind of correlations with no symmetry breaking states allowed if they could explain these signatures? That was what we wanted to explain. So the answer to this is yes. You will see how. So we are going to see that in the normal state, only with correlations, we can get a reorganization of the spectral weight, these cascades, okay? And of course, below, at lower temperatures, we will still have these broken symmetry states, that's for sure. But we wanted to see the normal state, because this is the normal state from which all these broken symmetry states is going to arise. So it's very important to understand what is this normal state. So in order to do this, we use dynamical mean field theory plus Hartree combination. I will explain why. And for this, we need a proper tight binding model for the Morel lattice. So let me introduce you first the model. These are the bands. The black lines are coming from a continuum model, the Brisider-McDonald model. And due to topology, these bands are topological, and even though these bands are well separated from the rest, and in principle you would expect that you can have a model only for these two bands, due to their topology you cannot do that. So one of the ways of creating a model that can fit these bands is to include more bands. So this is the approach that we took. In particular, we use an 8-orbital model proposed in this paper in the group of Caxiras, and the blue curve is the one that we fit with the Vanier model that we have. Okay, so you see very good agreement. This procedure allows us to keep the symmetries that we have in these systems. And in particular, we start from a continuum model. It looks very particle hole symmetric, but if you look very carefully, it's not completely particle hole symmetric, okay? Which is something that is known to be in real bands, no? Or to be expected. Okay, so these are the Vanier functions that we have. So we are talking about orbitals, but these are effective orbitals that live in the Moiré lattice, okay? So this is the Moiré lattice with the AA regions in which you have this AA stacking and then these AB regions, okay? And the orbitals that I'm talking about are effective orbitals that are huge. They cover many carbon atoms, okay? And these are the 8 orbitals. We have 3 orbitals in the triangular lattice. 2 of them have p symmetry, and 1 has S symmetry. Then we have the hexagonal lattice. We have 2 orbitals there, also with p-set symmetry. And then we have the Kagome lattice. Those are the purple ones. Okay, so these are the 8 orbitals that we have. And now if we look at how the orbital weight or the weight of each of these orbitals on the bands, we can see that the flat bands are basically dominated by only 2 orbitals, which are in the triangular lattice and have a p plus p minus symmetry, while the rest of the orbitals are dominating mainly the remote bands. And this is true everywhere except at gamma. Remember that I told you that we cannot have a model only for the flat bands, and this is the reason why you cannot do it, because you have mixing of all the orbitals close to gamma, okay? And this is important for the observation, in fact. Okay, now that we have the Vanier functions, we can calculate the interactions. So we calculate the Coulomb integrals, and this gives us these values. So this is the distance between the orbitals, and so this would be on-site interactions, and this is as a function of the distance, and you can see that we have a very long 1/r tail. So the long range interaction is also very important, and this is coming from the fact that our wave functions are very large, and they decay exponentially, but still they reach very far away. So all this tail has to be taken into account. And what we can see here is the following. The largest on-site interaction is coming from these orbitals that are mainly dominating the flat bands. So we have very small bandwidth and very large U. So these orbitals, we expect them to be very strongly correlated, while the others, they have significant U still, so it's not really very small, it's still significant, but the bandwidth is very large, so the interactions are less important. So this observation of having these 2 kinds of orbitals takes us to think that we can look at this as a heavy fermion picture, in which we have some orbitals that tend to form local moments and some orbitals that are itinerant, and they interact with each other. And in order to study this, we do some combination of techniques, theoretical techniques. So we use dynamical mean field theory to include the interactions and correlations for these orbitals, the ones that dominate the flat bands. And we use HAR3, which is a static mean field approximation that is very commonly used to study correlated materials for the rest of the interactions. So we don't throw away any of the interactions. We have everything here and only use dynamical mean field theory for the local interaction between the AAP, the most correlated orbitals. Okay? So dynamical mean field theory is very expensive technique computationally, so we cannot do it for the whole system, and so we did this effective way, and then we solve this self-consistently. Okay? And the most important thing is that even though this system would tend to have symmetry breaking states, we don't allow the system to have the symmetry breaking states because we want to see what you would expect only at the normal state. So we force it, okay? So before going to the results, let me explain a little bit or go back to some concepts, basic concepts, and see the kind of things that we should expect. So we start from mode, the simplest way of looking at the mode transition. So if you think of a lattice with a single orbital per side, that's the simplest, and we put one electron per side, that's half filling. So we have a Hamiltonian with two terms, the kinetic energy, which is proportional to the bandwidth, and the electron-electron interaction, which is proportional to U. So when you move around in this lattice, you save energy W, but that goes to energy U. So when U is much larger than W, you are going to have a mode transition. So for a half filling, in which you would expect to have a metal, you have an insulator. If instead of having one orbital, we have many orbitals, which is the case that we have here, then you can also have this mode transition happening at all the integer fillings in your system. So this is what we would expect. And very importantly, even when you are not at integer filling, you can have what I would call mode physics, which is strong effects of correlation, formation of local moments, etc. Okay, so you will have a metal, but this metal would have all these new features. Okay, so what kind of thing we would expect with dynamical mean field theory? Dynamical mean field theory includes the quantum fluctuations in your system. So this is again for a single band, half field case. When U and W are of the same size, then you have this density of states. This in particular would depend on the lattice that you have, the number of hopping terms that you put, whatever, but that doesn't matter. Qualitatively it's the same. So you have some density of states. And when U over W starts increasing, then you get this three-peak structure. The one in the middle is a coherent part, which is a heavy quasi-particle. And the two peaks that arise here are what we call the Haber bands, and they are incoherent. You will see what it means later. As you keep increasing U over W, this three-peak structure gets stronger, and at the end, you have this quasi-particle peak separated from the Haber bands. And when U is sufficiently larger than W, then you have a mode transition, and the quasi-particle peak disappears. So here you have a metal, and here you have an insulator. But here you have a very strongly correlated metal. Okay, so this is what you expect for one band at half filling with dynamical mean field theory. But the important thing here, again, I say that even when you are not in the mode when you are under the conditions for a mode transition, and in this area, you still have very strong correlations that are important. So in order to see how this goes, instead of going first to the TBG that I showed you that has 8 orbitals and is very complicated, I'm going to show you a simpler case, which is when you have ABC trilayer graphene on HBN. So this is not moiré, sorry, this is not twisted, but if you put it on top of HBN, then because of the different lattice parameter, you also get a moiré lattice, okay? In this case, it's much simpler because you apply an electric field and you have a single band, and with a particular direction of the electric field, this band is not topological, so we don't have this problem that we have with the twisted bilayer graphene, and we can have a very simple model to work with this. And in here, we also did dynamical mean field theory. Okay, so when U is 0, when there is no interaction, then we just have the band. Okay, This is the result that we will have. We just have the band that we expect from our tight binding. As you increase U, this is what happens. So this is what we were seeing before. The non-interacting density of states is something like this. That depends on the particular tight binding model that we have or on the system. And now, as we keep increasing U, you get the quasi-particle peak and the two Hubbard bands. And you can see here in the spectral function, this is like the bands that you would see if you can observe them, that the original band here has got really renormalized, so it's much thinner. And then there are this weight that is moving away from the chemical potential. And these are the Hubbard bands, okay? If you keep increasing U, you see this is exaggerated until the quasi-particle peak disappears. And this is the MOS transition. So for this case, we have a MOS transition at 28 MeV, okay? And you can see here how these Hubbard bands are forming and what it means, no? That your bands are not well defined. They have a finite lifetime. Okay, so let's go now to the results for our case. So remember that we have 8 orbitals, so it's a complicated system. And remember these cascades that I showed you before. This is the kind of structure that we would like to see if we can reproduce only with interactions, with correlations in the normal state. And this is the suppression of the conductance or the resistivity peaks that happen at interior fillings. And these are our results, okay? So this, we can see exactly the same features that were observed experimentally. We see the spectral weight reorganization. You see here these Hubbard bands forming and then moving towards the chemical potential and then resetting and going back. Okay, these are the kind of things that were observed experimentally. We also have these oscillations of the remote bands. We have a different behavior at charge neutrality point. You look here, there is like this kind of anti-crossing here. So we have everything that was observed in the experiments. And this is the same temperature at which these experimental measurements were done. So, okay, so this is the feature, a combination of these two. This is what sorry, yeah, I'm going back. Okay, so this is what we are observing here, okay? And also we can look at what happens with the density of states that will be as a function of the filling at the Fermi level. And we also see this a suppression of the density of states, that is what has been observed experimentally as well. But note one thing, that we don't have a mode transition here. If you look at the density of states at, for instance, -1, which is it has a very small density of states at the Fermi level. 0 would be the Fermi level. You see that we don't have a complete gap. Okay, so we don't really get a mode transition, and we will see why. We could also look at the inverse compressibility. That was the other measurement that I showed you that also have these resets. And we have the same features. We have this symmetric peak at the charge neutrality point and the asymmetric ones at other integer fillings. And about the resistivity states, we already saw that the density of states shows a very strong dip on the conductance, on the integer fillings, but we can also look at the conductance, and we see this same kind of result as was observed experimentally here. I mean, it depends on the samples, but this is the kind of general feature that you can get. So what is happening here different from what you would have for the simple case of only having one band? Here we have two kinds of orbitals. No? We said that we have these AAP orbitals that dominate at the flat bands, and they are strongly correlated. And we see that when we change the filling, the total filling, the filling of these AAP bands is increasing, but there are not really things happening at interior fillings. it's just increasing slowly. The other orbitals are having something that has this periodicity as a function of the filling. And this is happening because for the cases when you have integer fillings, there is when you get closer to that, there is more filling of these orbitals than of these ones on the derivative, because most of the charge is going obviously to the more correlated orbitals that are dominating the flat bands. The less correlated orbitals only appear because they have weight at gamma. Okay, but you see that we have the contribution of both kind of orbitals, and if you don't have all of them, you wouldn't get the cascades. I don't have them in the presentation, but I can show you if you want, that if you only consider these orbitals, you don't get the kind of cascades that have been observed experimentally. Okay, so and let's have a look now at the spectral function or the bands. So this is what we have at the charge neutrality point without, in which at the Hartree level, in which you don't have these effects of the quantum fluctuations. And this is what we have at the charge neutrality point with dynamical mean field theory. So we see various things here. We see these Hubbard bands that are coming from the moment, the local moment formation. We have also a momentum selective incoherence. So here we have, this is dominated, gamma is dominated by the less correlated orbitals. So they are much sharper, so they are better defined, okay? These are the itinerant orbitals. And so we can see here from this momentum incoherence, selective incoherence, that we have two types of electrons, no? These two types of electrons that we were talking before. Now, as you fill in, well, you see, you still have that. The bands here start to deform. This is coming from Hartree, the Hartree part of the interaction. And as you keep increasing towards 1, which will be the next integer filling, the heavy quasi-particle forms. Okay, and you still have, well, this incoherence that is forming. This is 1 already, so here we have something completely different, which is this like the bands restructure. Okay, and this would be what we can observe here in the density of states. If we go to the next filling, we will have something similar. So you see that this kind of behavior is repeating every time that you go to the next integer filling. If instead of doing dynamical mean field theory, we had only done the simplest mean field treatment, then we would have this, just something completely, just a deformation of the bands as a function of the filling. So this would be with charge neutrality point, and then when you go towards negative fillings, you have a deformation, and this is just monotonous, and the same in the other direction. And this is what we would have for the density of states. That has nothing to do with the cascades. There are no cascades there. Another way of looking at all this information, we can look at gamma, for instance, and then plot the spectral weight as a function of the filling. You can see that here at gamma there is a small energy signal or there are bands that are very close to each other. These two are coming from this part that is moving up and down because of the interaction at the Hartree level, in fact. And here we see the oscillations of these remote bands. We can also look at from other points. So at gamma, in fact, you would see that the signatures that you can get from, for instance, optical conductivity will tell you something about the distance in energy between the flat bands and the remote bands. And at M, which would be this, you would have signals coming from these Hubbard bands, okay? So the low energy part. and you can see in other directions just to get some idea of what you can get. And in particular, what we wanted to go now is to some probes, some other probes that can show that this picture of cascades coming from correlations is correct. So what we did is that we calculated the optical conductivity, in which, in fact, we can understand the results. It's very cumbersome, but you can see this is the filling again, all the integer fillings, and this is the optical conductivity, and there is this reset thing happening again, as we see in the density of states. And these signatures can be understood as coming from this transition. So optical conductivity, when you are, this is the Fermi level, so it would take you from below the Fermi level, above the Fermi level. So you can see that there are some areas that are going to be very incoherent, and this is going to give these areas in the optical conductivity that are not very well defined. And the places in which it is much more defined is because you have, well, these bands are much better defined as well. Okay, so you don't have this loss of spectral weight so strongly. We can also look at the low energy area, and we see here something that comes from this suppressions of the conductance at integer fillings, and then its effect at a smaller temperatures. So there are still no measurements of the optical conductivity, but we hope that with this we can also, I mean, when they are done, that we can learn from here whether these cascades are actually dominating the normal state as we think they are. Okay, so just to say that this work on these results are consistent with other techniques. So here they studied with it was a different model, so it was a continuum model, and they focus only on the flat bands and did a determinant quantum Monte Carlo, and they have the same kind of bands that we have at charge neutrality point. They only looked at the charge neutrality point. And then recently there has been a work in which they have used, they have done something very similar as we have done, but with a completely different model, the one proposed by Song and Bernabé. And all the results that are fulfilled with this like the density of states, the bands, and the inverse compressibility, when there is no symmetry breaking, are consistent with ours. Okay, so with this, I just finish. We have shown that we can have the cascades in the density of states at the normal state with no symmetry breaking. We have also made some predictions of how the optical conductivity should look like, and some ideas to get some information about this momentum selective incoherence that we have observed. And the inverse compressibility resets and the resistivity that increase at the integer fillings. And with that, I thank you for your attention.